Hello everybody, so today I will talk about the system design of Uber, and this is the second part of my video about Uber design. So in my first part, I did the high-level design. So I specified the function requirement and non-function requirement. And I set up this high-level design so that these function requirements are satisfied. And today I will talk how I can meet these non-function requirements. And especially I will talk about the matching process. So I kind of hand waved a little bit about this part. So in the system design, this is this part. So how Drive search service works, I will talk about that. And also, as I said, we need the strong consistency for matching to avoid the double matching. So I will talk about that. And then as a second topic, I will talk about the geospatial search. So for now, I put longitude, latitude data in user table and driver table, but the problem is how we can search the drivers who are nearby the user. So I will talk how we can optimize that query, and also scalability. So I specified this non-functional requirements. So I will talk how we can optimize this system so that this is satisfied. And also, as I said yesterday, the Uber system has a spike of the user request. Because, for example, if there was a kind of baseball game in the stadium, and after that, the users would like to order the Uber because they're so drunk and they can't drive a car. So in that case, maybe 10,000 or 20,000 users request the ride simultaneously. So I will talk about that spike too. Okay, so I will talk about the matching process. So as specified here, user makes the request and driver receives a push notification about the nearby request. And driver can accept the request and matching with the user. So how should I work on this? So firstly, I have to clarify about this functional requirement a little bit more because so the idea is it is possible that, let's say, there is a user and user makes a request. Let's say user is in California, Los Angeles downtown. It is possible that the Uber system makes a push notification to all the users in the downtown Los Angeles, which means that all the nearby drivers, and one of the drivers accepts the ride, and the first driver gets a match basis. So this is possible, but this is quite a bad experience for drivers. Because let's say the push notifications are sent to, let's say, 100 drivers, and one of them gets a match, but others, even if he accepted, if he's second or later driver who accepts a match, that accept, how should I say, request fails, and he ends up without matching. So this is a bad request for driver, so I have to think of a better way. So I think what I can suggest is, so let's say push notification is sent to only one driver, but the driver has a very short period, like 5 seconds, to accept it. So if the driver, cannot accept the ride within that period, he loses the opportunity for the match. And the next driver, push notification will be sent to another driver, and another driver has now has the chance to accept the ride. So what I mean to say is the kind of possibility to match is given to only one, or I should say chance to match is given to only one driver at a time. And it is repeated every 5 seconds. So I would say 5 seconds. To, or just a response the request, and up to 12 drivers, or I should say maybe maybe I will use some buffers, so I should say this is repeated for 1 minute until okay, this is it. So I will talk about how I can meet this functional requirement actually in this driver search service. Oh, and one more thing I have to say is driver is given 5 seconds to respond the request. So what is important here is only one driver. Okay, there is a request, and at the same time there is up to one driver who is given the chance to match. But driver's side also has to make sure that no more than 2 requests are sent to the same driver with the push notification. So driver so I will also include this in the functional requirement of this, feature. Okay. So what I can do is, let's say there is a change data capture when the request is created for this, let's say user ID number 1. And what this driver search service can do is kind of get the stack of drivers who are nearby by making the geolocational query to driver. Let's say it gets 100 drivers. And then this driver search service, one by one, sends a push notification to the driver. But there is some problems here. So I think this idea works, but the problem is, let's say, maybe here, driver is given 5 seconds to respond to the request. So okay, maybe I should write this one first, because the order-wise, this occurs first. So driver receives at maximum requests at the same time. How can I guarantee this? So something maybe I can do is, let's say I use a kind of lock. So one driver is giving only one request. So maybe I can do something like this: request ongoing, or maybe checking request ID. So the idea is I use the row lock here. So wait a minute. So this driver service, okay, to get stack of nearby user drivers. So what did I say? Yeah, takes the rock, then gets the rock of driver. But also I have to take care that I need the rock for the user too. So I assume that we use the raw rock of PostgreSQL, but I will talk about this. Wait. Maybe I can say checking driver ID. Wait. Maybe I want this in the request table. Yeah. So the thing is, gets the rock of driver and gets the rock of yeah. So gets the rock of driver and also gets the rock of request. So in this way, what happens is that so if it fails to get the rock of the driver, you know, the driver is currently matching, so it doesn't work. And also for request, if wait, request. No, sorry, I think I don't need this because one request is handled by one service. So as long as this service does the, request matching sequentially, this much isn't needed. Okay. But now I just noticed something. So of course I have to make sure that if the driver is currently working or not. So we need status like working versus a waiting or driving. Yeah. Or maybe I should say available driving or as a status not working. So offline. So if the driver status is available, I can say this driver search service can take the rock of this driver row, and change the status to driving, and then the match is wait. So I actually need one more status here. Matching. Yeah. So okay. Firstly, this driver switch service checks the driver table, and if status is available, it takes the rock and updates it to matching. And then commit versus finish the transaction, and this status changes, committed. And then this driver search service makes a push notification to the driver, and then driver makes a request to accept it or not. And of course, this matching status is kind of has a time limit. So if more than 5 seconds has passed, this should be reverted to available. And even if the driver sends the accept request, it should not match. Okay. So it's a kind of process I can use. So maybe the idea is the most important part is I use the raw rock or I should say, at least I have to make sure that the strong consistency is needed. Yeah. So I make sure that strong consistency, but here the strong consistency I discussed is about the driver's status, or I should say driver's you know, sorry. So it's a kind of matching game. So what I've talked about the matching is driver search service with driver. And now with this rock, driver matches only with one request notification. So now driver is not sent more than one request at the same time. So, but I also have to guarantee the kind of strong consistency on the matching too. So I will talk about that. So okay, when it matched, the ride is created. But I think what I can do here is almost the same. This request status, I will use the row rock of request row 2 so that more than 2 client reads the request status and update to it to match optionally. So those transactions should be done sequentially. So in that way, I can also guarantee the match. Okay, so what I can do is, okay, here. Oh, maybe I didn't write something here. Submit driver response. Oh yeah, this one. So this one should be done with the row rock and make sure that this is made sequentially. Yeah. Okay. So I said I use the row rock, but I didn't explain why I use the row rock. Because there are some ways to guarantee the strong consistency. Let's say I can use the PostgreSQL isolation level linearizable. Serializable. So in that way, each query, all the queries are handled one by one. So it tracks the queries are waiting in the waiting queue one by one. But this worsens the overall performance of the relational database query, so I don't use it. Also, I would say I think I can use a kind of optimistic rock, but here I don't use it because what should I say? Optimistic rock needs a more kind of, what should I say, custom implementation. Like we need the version key in drivers table and the request table, so it has more implementation cost. And all the more, in this case, basically, how should I say? Yeah, for request status, because there is only one. Yeah, because there is only one match. So, wait a minute. Okay, so I will use the pessimistic rock with row rock here, and I don't use the optimistic rock. This is because optimistic rock with the version key is not suitable for the situations that there are many contentions, because in the case of optimistic rock. If let's say there are multiple clients who'd like to take the rock, and if one of them can rock it and update the version, others fail and others have to retry and retry until it get it. And in the case of Uber matching, it is possible that there are many contention. So let's say there are so many users in the specific area and there aren't so many drivers. This is typical in the case of, let's say, stadium after the concert. Yeah. So in that case, there are many users who try to get the rock of the one driver. So the contention is quite intensive. So in this case, I use the pessimistic rock. So yeah. Okay. So that being said, yeah, so this is it. And one more thing I have to discuss here is the kind of problem, which is, let's say, who update this driver status from matching to available after 5 minutes. Sorry, 5 seconds. So let's say driver search service would like to do it. But let's say driver search service server dies. In that case, it cannot revert the matching to available, which means that that user status doesn't change from matching. So if that driver, what should I say? If that driver doesn't respond, the status doesn't change from matching. Yeah, of course, I can kind of do the implementation like if driver request response is reject, this matching should be reverted to available. But yeah, I don't. Okay, but of course, if the driver doesn't respond, it cannot possible. So the idea is I use the kind of timestamp row here. So here I put something like match until timestamp. So in this way, this driver search service can know if this is really locked or not. So really matching or not. So this driver search service should make the query to know if this driver is matching or not by status is available or status is matching and current time is less than or equal to matched until. Yeah, sorry, matching until. So in this way, even if this driver search service dies, another driver search service, which is booted up for this user, can know if the driver is really matching still. Okay. Okay, so I will quickly summarize what I told. So for this driver search service, what it does is, so firstly, get the stack of nearby drivers. So with buffer, let's say I take maybe 30 drivers. Yeah. And then for each driver, let's say every 6 seconds with buffer 1 second. So firstly, check if this driver is available, and if it is true, update to driver status matching. and also timestamp. So okay, so in this way, this takes the rock. So of course I have to do for this one, I use the select for update query so that it can take a rock. And then after this is done, of course, yeah, this is done in the transaction, database transaction. And firstly gets the rock of this driver with select for update statement. And then if he's available, it updates driver status to matching and match until timestamp to 5 minutes later. Well, yeah, of course, this needs something like this, or of course, status is matching, but match until is greater than now. In that case, this driver is available, so you can take rock and update in this way. So now this driver's log is acquired. So driver search service sends the push notification. Then this driver makes, let's say, accept it. So I will talk about the happy scenario. Accepts request. So now what happens is that this driver has the chance to match with the right request with the user. So of course, matching service does the validation. Or maybe I can do update query with let's say I can use the where query. So updates the row whose request ID is something, and driver is something, and matched until is less than current time. With this where query, the driver is filtered and found only if matched until is before now. So I can use it. So now driver accepts the request and server side. Match service. Update driver table, driver status. And as I said, driver status, and if it succeeded, create write query, so write recode. Yeah. And also response, driver response. Yeah, this should be created. Even though this is not the most important thing. This is it. But wait a minute. Yeah. So in this way, yeah. Okay, good. Yeah. There's no double matching here, because as I said, only this server works on the user, some user ID, let's say 1. So there isn't any other concurrent user who's looking for the match for driver user ID number 1. So as long as this driver search service sequentially sends a push notification to the driver, and I make sure that we set the correct match until timestamp, and the server side rejects the match request, or I should say, accept request if it's time over, then I can say double matching doesn't occur. So that's the kind of thing I can use here. And maybe one more thing I'd like to say is, for the case if this server dies, let's say I would create matching until. So in this way, what should I say? Wait. If this server dies, there is another server which inherits the matching process for that user ID this server was working on, and then it can work until write time becomes unavailable. So of course, this server has to get the matching until timestamp only at the beginning and do this process by for loop until time out. Yeah, of course, maybe there is a kind of discussion that how, in the case if this server dies, the next server know which driver IDs user IDs, or I should say request IDs are handled by this server, but maybe I can use the job orchestration or something like that to make sure. And sorry, this is not here. This should be here. Okay, so now we'll talk about the second topic, geospatial search. So I did the geospatial search here. So query to get stack of nearby drivers from the driver search service. So of course, it firstly takes a look at the user's current longitude, latitude, and then makes a query. So, by the way, as a premise, user is not riding the car, so user's location doesn't change a lot. So, especially within a minute. So, this user's current location has to be fetched only once, and then from that, I have to make the query to drivers, location. So what can I do here? So as long as we use the PostgreSQL and I try to make it with the minimum effort, I can use the PostGIS extension. So the thing is, PostgreSQL has the column type named point. So with that point, I can create PostgreSQL can handle the query with the geolocation. Yeah, so, but of course, the thing I will do is makes a query with longitude, latitude range, and then PostgreSQL fetches us a point with those. And of course, I have to make sure that the drivers are in the radius, let's say 20 miles, maybe 10 miles. So, of course, with the where statement, I will do a kind of x gap, x diff squared plus y diff squared is less than max radius squared limitation, or I should say filtering. But that's a kind of possible way to do it. Yeah. But I don't do it from two perspectives. The first perspective is this PostGIS extension uses the R tree. So R tree is a kind of tree structure. I talked about this R3 in my previous video, but I will explain quickly. So R3 looks something like this. So the whole area, I mean, this is a tree structure, and the whole area is firstly put into the single node. And oh, by the way, only the single node, sorry, leaf nodes has the reference to the data point. So these branch nodes doesn't have the reference to point data. It's quite similar to B tree. Yeah. So that being said, firstly, there is only one single node, which is leaf node and also root node, and that node has all the point references. But this R3, as there are many points, it creates a kind of smaller box, leaf box, sorry. Oh, wait. Then it does for each area. So, and this actually creates the tree in a bottom-up way. So if there are many points here, it creates a small rectangle, or I should say, what should I say? So small rectangle, minimum boundary box. So if there are many points here, it creates the minimum boundary box, and from there, I create the larger box which contains multiple child boxes. So again, this parent box is the minimum boundary box of the boxes, and then I repeat it until the root node. Of course, there are so many boxes here. The child parent box should contain many more boxes. So in that way, this R3 is balanced tree. So query performance is stable. But the problem here is, sorry, this one. The problem here is because this is a tree structure, if point here moves, let's say point around here, other area, I have to restructure the tree. Of course, the move is very small and infrequent. It isn't a big cost, but if the location of the point moves frequently and intensively, I should say, and also long distance, it becomes a problem. And in case of Uber, this completely meets exactly this situation, because driver moves very first with a car, and it moves to many drivers, basically moves around. So R3 is not the best fit for Uber design, especially geospatial search of Uber. So what I will use is another geospatial index named GeoHash. So GeoHash looks something like this. So firstly, the whole world is separated into 4, and each area is divided into sub-area recursively, and each smallest tile has the same size. And every time the tile is, or I should say, area is divided into sub-areas, the number is given, and the number, or I should say digit, is added as the suffix. So for example, for this 00 area, this is divided into 4, and it has the suffix 0, 1, 2, 3. Yeah, for these 4 tiles. So in this way, the world is separated into the same size of tiles. And let's say I'd like to search around here, 033 somewhere. It has to take a look at this 033, and optionally the adjacent cell adjacent tile if the search area is, has the intersection with 031 cell. So database engine can convert the search center location into the tile number very quickly with the calculation, and also it can clarify which tiles it has to check quickly. And each point holds this, or I should say each row has the hash value as the another column, special column. And the database engine creates the B tree with this hash value. So in this way, once the tiles to be checked, tile hash values to be checked is clear, now the database engine can quickly know which point belong to 013, which point belong to 031. Yeah. So it can do it with log n time to find the first point in the B tree index, and then linear scan all the point in that tile. So this is what happens in this geohash. Yeah. Okay, and geohash is very good other use case of the Uber, because geohash has a strong point that it is performant for it to handle the update query of the location. So it is because in the case of geohash, if the XY value is updated, all it has to do is update the X column value, Y column value, and also the hash value recalculated. So it is much more performant than the update query of R3, which may have to restructure the tree structure. Yeah, and also geohash performs very well for the geosearch query, read queries. Yeah, because it has to take a look at a limited number of tiles. Yeah, if it is around here, it only has to take a look at one tile, but maybe if it is on the boundary, it has to check maybe a few more tiles. But in either way, the limit, tiles to be checked is limited, and of course database can do the search in each tile concurrently, so it performs good. So I can use the R3 here, geohash here. So instead of this longitude latitude in the user table, I will use the geohash database. So PostgreSQL PostGIS is using R3, so I use the kind of another database here, and here I can use the Redis, because Redis has the geolocational geospatial index based on the geohash. So with this, this query should go to Redis geohash. Here. Okay. So this goes first. Yeah. Okay. So yeah, and of course we don't need longitude latitude here anymore. Okay, so actually this Redis geohash is good because and the query should go here. This is actually beneficial in one more perspective. So in case of Uber, as I said, the update query of the location is quite intensive, and it overloads the server. So in the case we use the PostgreSQL, the load by this updated location query may impact the database queries for other, features. So it is a good idea that I separate the database, and because Redis is the in-memory database, it's much more performant than the PostgreSQL, which persists the data in the storage. So in that perspective, Redis geohash is good too. Okay, so that about the Redis geohash and geospatial search. But there's one more thing I want to mention. So this Redis geohash, splits this area into squares. No, so rectangles, yeah, not necessarily squares. So, but because the Earth has a curve, this rectangle doesn't, completely fit the Earth. So to handle this, Google develops the geospatial index named S2, and Uber invented H3. And in H3, H is the acronym of the hexagon. So as you can see here, the world is covered by hexagons, and each hexagon has the internal hexagon recursively. So that's the S3 index. And of course, because we have to handle the geospatial query on the Earth, I use the H3 index instead of geohash. Okay, so this is all about the geospatial search. Okay, so now I've talked about the first topic, matching process, including strong consistency, and number 2, geospatial search. So I wanted to talk about scalability too today, but I'm so tired today, so I will talk about this in the next video, in part 3. Okay, so that being said, I finished my today's system design practice. Thank you so much. Bye bye.